On February 25th, 2026, something happened that genuinely should not be possible. A historic blizzard ended, and the number of simultaneous National Weather Service alerts across America went up, not down, up. 616 active warnings at the same time, more than during the blizzard peak itself. Hurricane winds in Alaska, 90 degrees in Southern California, 20 inches of snow and 83-mile-per-hour gusts in Colorado, simultaneously, 100 miles apart. A moisture anomaly so statistically extreme it shows up roughly once in 3.5 million observations. One pattern, every direction, all at once. And if you think these are 5 separate stories, you are wrong, because this is one story with 5 faces. Stay with me. If this has you pulled in, hit subscribe, because this pattern is still evolving and we are not done tracking it. Drop a comment telling me where you are watching from and whether any of this is hitting your region right now. And if you want to help the Skylab grow, share this one. You are the reason we can keep doing this. Now, let's get into it. 616. That number was sitting on a screen at the National Weather Service on February 25th, 2026, and it was still climbing. Not 616 warnings for one storm. Not one type of hazard stacked up from one system grinding its way across the country. 616 simultaneous active alerts, hurricane-force winds, wildfire conditions, river floods, blizzard-class snow and temperature extremes all live at the same time, all across the United States, all on a single Wednesday morning. Here is what makes that number genuinely strange. Just days before, the eastern seaboard had been buried under one of the more dramatic blizzards in recent memory. Alert counts had surged to around 550 as that system peaked, which was already a significant number. Then the blizzard ended. The snow stopped falling on Boston and New York. The emergency declarations got lifted, and the alert count did not drop. It went up, from 550 to 552 as the blizzard wound down. And then, instead of falling back toward baseline, it kept climbing. 616, by the time we're talking about it now, that is not how this is supposed to work. When the storm that drove the alerts ends, the alerts end. The count falls. The atmosphere takes a breath, except this time it didn't. And the reason why tells you everything about what is actually happening to the American atmosphere right now. This is not 5 separate weather stories happening to coincide on the same day. It is one story, one amplified atmospheric structure, expressing itself in 5 radically different ways across 5 radically different regions. The blizzard didn't resolve. It transformed. The same pressure configuration that buried the East Coast redistributed its energy, and what you're seeing now is the result. A pattern that didn't calm down, it just changed faces. Let's paint the picture quickly, because the scope of this matters. In the Gulf of Alaska, the National Weather Service was issuing hurricane-force wind warnings, not metaphorical ones, actual sustained winds above 64 knots over open water. Southern California was looking at forecast highs approaching 90 degrees Fahrenheit in the last week of February. Northern California's rivers were pushing toward flood stage, with the Eel River already breaching moderate flood levels. In Colorado, a single ridge running along the foothills was simultaneously recording 83-mile-per-hour gusts at a site called Dakota Hill, producing near-record warmth of 71 degrees in Denver and dumping 10 to 20 inches of heavy wet snow across the Park and Medicine Bow ranges, all within 100 miles of each other. The Central Plains and Rockies were under red flag fire warnings. The Northeast, still sitting under a cold dome left over from the blizzard, was getting clipped by lake effect and shortwave snow systems. And up in space, but we'll get to that. How does a weather system produce 90-degree heat and 20 inches of snow at the same time? How does the alert count go up after the storm ends? And what does a ridge-trough configuration actually have to do with any of this? The answer is a concept called the pressure gradient superstructure, and once you see it, you cannot unsee it. The physics here is not exotic or controversial. What we're watching is textbook Rossby wave behavior, the planetary scale atmospheric waves that organize the jet stream into ridges and troughs, into high pressure domes and low pressure channels. Rossby waves are always there. They are always shaping weather. What is not always there is this level of amplitude, this degree of contrast between the ridge and the trough, sustained across this many days, producing this many simultaneous extremes at this level of intensity. The mechanism is understood. The magnitude is the story, and the magnitude is what we need to talk about next, because the 100-degree temperature spread sitting across the continental United States right now is not just a dramatic statistic. It is the engine. It is the fuel. It is the reason 616 alerts are active simultaneously, and it is the reason the count keeps climbing instead of falling. What the atmosphere does with that much thermal contrast, what the jet stream does when it has that much energy to work with, is where this story gets genuinely unsettling. There is roughly 100 degrees Fahrenheit of temperature difference sitting across the continental United States right now, and that number is not a curiosity. It is a structural condition. It is the thing that makes everything else on that 616 alert board possible, and it is worth pausing here to understand why, because most coverage of extreme weather treats heat and cold as separate stories, as opposing teams, as things that cancel each other out. They don't. In the atmosphere, they amplify each other. Think of the atmosphere as something that desperately wants to equalize. Hot air on one side of the continent, cold air on the other, and in between, a pressure gradient that the physics of fluid dynamics will not allow to sit still. The pressure gradient force, stated simply, is the force that drives air from regions of high pressure toward regions of low pressure. The steeper that gradient, the more compressed the distance between extreme cold and extreme heat, the more violent the response. You can write it as a relation. The force equals negative the gradient of pressure. That's it. Tighter gradient, stronger force, stronger winds, more lift, more energy available to the system. What that means in practical terms is this. The 83-mile-per-hour gust recorded at Dakota Hill in Colorado on February 25th was not produced by some rogue local wind event. It was produced by an exceptionally steep pressure gradient between a ridge of warm, high-pressure air parked over the western United States and a deep trough of cold, low-pressure air digging into the central and eastern portions of the continent. The tighter that boundary, the more compressed that gradient, the faster the air accelerates across it. Colorado just happened to be sitting directly at the inflection point, which is why Colorado got all three extremes at once, but we'll come back to that. The same gradient that generated those wind speeds is doing other things simultaneously. Over the Colorado Rockies, air moving rapidly from west to east gets forced up the western slopes, cools, saturates, and drops enormous amounts of precipitation, which at altitude in late February means snow. But the same air that rises on the west side of the mountains descends on the east side, compressing adiabatically, warming at roughly 5.4 degrees per 1,000 feet of descent. That's compressional warming. That's why Denver was approaching 71 degrees while the mountains 40 miles west were measuring snow in feet. Meanwhile, that same pressure configuration was extending its reach. The jet stream, channeled and accelerated by the thermal contrast between the ridge and the trough, was delivering a moisture plume into northern California, a corridor of atmospheric water vapor that river basins along the Eel, Russian, Navarro, and Sacramento don't have the infrastructure to absorb all at once. At the same time, Southern California was sitting under the warm, subsiding air of the ridge itself, insulated from moisture, baking at temperatures that belong in May. In Alaska, the deepening low-pressure system in the Gulf, the one generating hurricane-force winds over open water, was being fed by the same extended Pacific jet that the ridge-trough configuration was stretching and intensifying. The cyclone didn't appear in isolation. It appeared because the upper-level trough provided the divergence aloft needed to spin up a powerful surface low, which then had an enormous fetch of open ocean to work with. Every one of these events, the Colorado gusts, the California split, the Alaska marine storm, the Northeast cold dome, the plains fire danger, traces back to one root condition: an amplified planetary wave sitting over North America with a temperature contrast large enough to generate jet stream winds and pressure gradients of unusual intensity across thousands of miles simultaneously. And here is the part that should make you want to keep watching. That temperature contrast, that 100-degree spread, doesn't just produce the extremes we've already talked about. It produces anomalies at the statistical edge of what our models even account for. One of those anomalies showed up in a single column of air over Colorado, and it measured 5 standard deviations above normal. If you know what that means statistically, you already know why that number matters. If you don't, give me 90 seconds in Act 2, because it reframes everything. But first, Colorado, 100 miles. Colorado, 1 Three simultaneous extremes that by every reasonable expectation should not coexist. Let's go there. If you want to understand what a single amplified pressure gradient can actually do to a landscape of human infrastructure and lived experience, you don't need to look at the whole country. You just need to look at a 100-mile strip running from the Colorado foothills into the Park and Medicine Bow Ranges on February 25, 2026. At Dakota Hill, located in the foothills west of Denver, instruments recorded a gust of 83 miles per hour. To be clear about the magnitude of that number, that is hurricane-equivalent wind speed at a land location in February. Those winds, driven by the steep gradient between the ridge-induced high pressure to the west and the trough-reinforced low pressure digging east, were accelerating air down the eastern slope of the Rockies in what meteorologists call a downslope windstorm, a process where air descending the lee side of a mountain range compresses and accelerates, sometimes dramatically. The Front Range of Colorado is particularly prone to this under the right synoptic setup, and February 25, 2026, gave it about as favorable a setup as it gets. Those same winds, combined with the warm, dry air being advected eastward off the mountains, pushed relative humidity into single digits across the foothills and plains immediately east of the Front Range. Red flag conditions, the threshold at which fire can spread rapidly and unpredictably, were triggered across a wide swath of the region. This is not a theoretical fire risk. This is the kind of conditions that have ignited some of Colorado's most destructive fires in the last decade. Fires that have burned through communities in hours. The gradient that was producing record warmth at Denver International Airport was simultaneously turning the foothills into a tinderbox. And Denver itself, 40 miles east of the mountains, sitting on the high plains at 5,280 feet, recorded a temperature approaching 71 degrees Fahrenheit on February 25th. That is a near record high for the date. That warmth is not mysterious. It's the product of air descending from the mountain crest, compressing at a rate of about 5.5 degrees per 1,000 feet, arriving on the plains 20 to 30 degrees warmer than it started. Denver's weather station measured the thermal signature of adiabatic descent almost perfectly on this day. Now go 40 miles in the other direction, west into the mountains, into the Park Range and Medicine Bow. At the same moment Denver was approaching 71 degrees, the mountains were measuring snow accumulation in feet. National Weather Service Denver issued forecasts of 10 to 20 inches of accumulation across the higher elevations, with some areas potentially exceeding that under the most favorable orographic enhancement zones. These are ranges that can absorb significant snowfall, but the character of this snow matters. When air is warm and saturated, when the moisture content of the atmosphere is as anomalously high as it was on this day, snow ratios drop below 10 to 1. That means for every inch of snow water equivalent, you get less than 10 inches of snow. The result is heavy, wet, dense snow. The kind that snaps tree branches under its own weight, collapses roofs, and triggers wet slab avalanche conditions on steep terrain. Colorado's Avalanche Information Center was watching this closely for good reason. All three conditions, the 83-mile-per-hour gusts, the red flag fire danger, the heavy mountain snow, were being produced by a single shortwave trough moving through the amplified pattern. Not three separate systems, one gradient, one structure, three simultaneous emergencies in 100 miles. The reason this matters beyond Colorado is that it illustrates something fundamental about how this pattern is operating nationally. The same dynamic that split Colorado into three simultaneous hazard zones is playing out at continental scale. The ridge and the trough are not being polite enough to keep their hazards geographically separated. They are stacking them, concentrating them, generating conditions at locations that sit directly at gradient boundaries, and those boundaries right now happen to cut through populated regions with complex terrain and aging infrastructure. The National Weather Service office in Denver explicitly flagged something in its meteorological discussions that stopped people in the forecasting community: a precipitable water anomaly measuring approximately 5 standard deviations above normal. 5 sigma. That phrase means something very specific in statistics, and understanding it is going to reframe everything we've covered so far, including why 616 alerts is a number you should not be comfortable with. Let's go deeper. Precipitable water is a measurement of how much water vapor is present in a vertical column of atmosphere from the surface all the way up to the top. If you could condense all of that vapor at once and let it fall as rain, precipitable water tells you how many inches of rain you'd get. It's a direct measure of how much moisture the atmosphere is carrying at a given location. On February 25, 2026, the precipitable water value over portions of Colorado was approximately 5 standard deviations above the climatological normal for this date and location. The National Weather Service called it out explicitly in their technical discussions, which means it was anomalous enough that operational forecasters felt obligated to flag it for their colleagues. Here's what 5 standard deviations means in statistical terms. If atmospheric data were perfectly normally distributed, a bell curve, the probability of a value falling 5 standard deviations or more from the mean is roughly 1 in 3.5 million. You'd expect to see it, by chance, once every 3.5 million observations. Now, atmospheric data are not perfectly normal. Tail events occur more frequently in geophysical systems than a simple Gaussian model would predict. But even accounting for that, when NWS flags a 5 sigma signal, they are not doing so casually. They are telling you that the moisture loading in this column of air is genuinely exceptional, not just unusual for the season, not just above average, but statistically extreme. The z-score calculation is straightforward. Subtract the climatological mean from the observed value, divide by the standard deviation. A result of approximately 5 means the observation sits 5 standard deviation units above what is typical. Even with fat-tailed atmospheric distributions, a z-score of 5 represents a signal that is hard to explain by random variation alone. So where did that moisture come from? The answer connects directly back to the central structure driving all of this. An atmospheric river, a narrow corridor of concentrated water vapor transport from the tropics and subtropics, was being channeled inland off the Pacific and aimed directly at California and the broader Southwest. As that moisture plume encountered the topography of the Sierra Nevada and the Rockies, and as the dynamic lifting associated with the trough's passage maximized vertical motion at exactly the right location, the moisture was squeezed out of the atmosphere in extraordinary quantities. The alignment of moisture transport, topographic forcing, and dynamic lift was nearly optimal, which is exactly the kind of convergence you'd expect from an amplified ridge-trough configuration with a steep pressure gradient providing the mechanical forcing. Whether atmospheric river interactions with the Rockies are intensifying over time is a question researchers are actively working on. The data are suggestive in some studies, but this is not a settled question, and one event proves nothing. What we can say about February 25th is that the moisture anomaly was not random. It was generated by the same amplified wave pattern producing every other extreme on the board. The 5 sigma signal was not an independent curiosity. It was a symptom of the same engine we've been tracking since the first alert number appeared on that screen. And that engine was doing something remarkably similar, thousands of miles northwest in one of the most hostile marine environments on Earth. While Colorado was trying to manage 3 simultaneous emergencies within 100 miles of each other, the Gulf of Alaska was experiencing something that would dominate headlines anywhere else on the planet. 6 separate hurricane-force wind warnings issued simultaneously across the marine zones, with sustained winds of 55 to 65 knots and seas running 17 to 20 feet or higher. Those are not tropical hurricane conditions. Hurricane-force wind warnings. In the marine context are issued when sustained surface winds meet or exceed 64 knots over ocean water, the same wind speed threshold that defines a tropical hurricane by the Saffir-Simpson scale, but without the warm core structure, the spiral bands, or the tropical origin. What the Gulf of Alaska storm had instead was an extratropical cyclone that had undergone rapid deepening under the influence of the upper-level trough extending from the same Rossby wave arc, affecting the lower 48. The divergence aloft associated with the trough provided the atmospheric evacuation that allowed surface pressure to drop quickly, spinning up a powerful surface low over a body of water with enormous fetch, meaning the wind had a very long, uninterrupted run across open ocean to build waves. 17 to 20-foot seas are what you get when you combine hurricane-force winds with that kind of fetch over an already rough water environment. The severity rating on these warnings was extreme with immediate action required, the highest tier available. And accompanying those warnings were 84 heavy freezing spray warnings, which was the single largest count of any warning category in the entire national inventory that day. Freezing spray at a rate of 2 centimeters per hour or more accumulates on vessel surfaces rapidly enough to alter a ship's buoyancy and stability. It is one of the leading causes of vessel loss in high-latitude marine environments. 84 simultaneous warnings of that type represents an extraordinary marine threat across the Gulf. Geographically, there was also a magnitude 6.1 earthquake recorded near Nikolsky, Alaska, around this same period, not causally related to the storm, but notable as a reminder that the region the storm was affecting is simultaneously one of the most seismically active and meteorologically hostile environments in the Northern Hemisphere. The Gulf of Alaska storm gets a fraction of the attention that a comparable event in the Gulf of Mexico or Atlantic would receive, partly because of its remoteness and partly because its impacts fall primarily on commercial fishing vessels and cargo ships rather than on densely populated coastlines. But the atmospheric significance of that storm is not remote at all. It was the Pacific expression of the same hemispheric Rossby wave arc that was simultaneously producing fire danger in Colorado, flooding in California, and anomalous warmth across the Southwest. The ridge-trough pattern doesn't have borders. It doesn't respect coastlines. It stretched from the Gulf of Alaska all the way to the northeast residual cold dome, and every extreme we've discussed lived inside that same wave structure. Which brings us to the state that was being cut cleanly in half by the boundary between the ridge and the trough on February 25th. A state that was simultaneously flooding in the north and approaching record heat in the south. California, as usual, had the most dramatic expression of the pattern's internal contradiction. California gets split by weather patterns with some regularity. The state is long, geographically complex, and climatologically diverse enough that northern and southern California can experience genuinely different weather simultaneously on a normal week. But what was happening on February 25th, 2026, was not a normal split. It was a demonstration of the same ridge-trough boundary that was already bifurcating Colorado and separating the marine environment of Alaska from the conditions in the lower 48. In Northern California, the rivers were running hard. The Eel River was already at moderate flood stage, with water levels threatening infrastructure and prompting emergency managers to issue evacuation advisories in portions of Humboldt County. The Russian, Navarro, and Sacramento rivers were at or approaching minor flood stage, with upstream gauge readings suggesting conditions would continue to rise through the afternoon and overnight hours. The moisture plume feeding these river systems was the atmospheric river we talked about in the context of Colorado's precipitable water anomaly, the same corridor of water vapor transport that was loading the atmosphere at 5 standard deviations above normal over the Rockies was first making landfall in Northern California, releasing massive quantities of precipitation over terrain that funnels water into those river basins quickly. Atmospheric rivers are, in their basic structure, relatively narrow corridors, typically a few hundred miles wide but potentially a few thousand miles long, that transport water vapor poleward from the tropics at rates comparable to or exceeding the average flow of the Amazon River. When they make landfall against the coastal mountains and Sierra Nevada, the forced descent extracts that moisture rapidly. Northern California is well adapted to atmospheric river events in general, but the intensity of this one, amplified by the anomalous moisture loading documented in the precipitable water data, was pushing beyond what drainage infrastructure could readily handle. Then you drive south, not even that far south, relatively speaking. Cross the Sacramento Valley, get into the Central Valley foothills, keep going south past the transverse ranges, and you emerge into a completely different atmosphere. Southern California on February 25th was sitting under the warm, dry, subsiding air of the ridge. Subsidence, the slow sinking of air from upper levels of the atmosphere toward the surface, compresses air adiabatically, warming it and suppressing cloud formation. The result was cloudless skies, low humidity, and temperatures in the middle to upper 80s across the Los Angeles basin, with some inland valley locations approaching 90 degrees Fahrenheit in the last week of February. A temperature of 88 to 90 degrees in late February in Southern California represents an anomaly of more than 20 degrees above the climatological normal for the date. 20 degrees above normal is not a warm day. 20 degrees above normal in a compressed late winter atmosphere over a region already in fire season year-round is a different category of concern. The gradient between the moisture-loaded flooding north and the hot, dry subsiding south was sharp enough that you could, in theory, drive through it in a couple of hours, transitioning from flood emergency to heat advisory without stopping for gas. The sharpness of that boundary is itself a signature of pattern amplitude. In a more typical winter pattern, California's weather regimes blend and transition gradually. When you have an amplified ridge sitting hard against a well-defined trough, the boundary between them becomes compressed, a narrow zone where atmospheric conditions change rapidly over short distances, and where the hazards on either side are simultaneously at extreme values. Is ridge persistence increasing over the western United States? Some research has pointed toward a connection between Arctic amplification, the accelerated warming of the polar regions, and the tendency for high-pressure ridges to become more stationary over the West Pacific and western North America. The hypothesis is that as the Arctic warms faster than the tropics, the temperature gradient that drives the jet stream weakens, and the jet stream responds by developing larger, slower-moving meanders. Larger meanders mean higher amplitude Rossby waves. Higher amplitude waves mean more persistent ridges and troughs, held in place longer, compounding their impacts on the regions beneath them. That hypothesis is contested. It is not settled science. There are atmospheric scientists who argue persuasively that natural variability, particularly interactions between the El Niño Southern Oscillation and the Pacific Decadal Oscillation, can produce patterns like this without requiring any change in background climate state. Both positions have peer-reviewed support. Neither has definitively won the debate. What we can say with confidence is that on February 25th, 2026, the ridge was there, the trough was there, the boundary between them was cutting California in half, and the same pattern was simultaneously running the rest of the alert board, all 616 items on it. And 93 million miles away, something was adding a layer to this story that is either a remarkable coincidence or a question mark that science has not yet fully answered. The solar disk on February 25th, 2026, was nearly spotless. Active regions were minimal. Solar flare probability, the chance of a significant X-ray burst from a solar eruption, was sitting at 0%. By the standard measure of solar activity, this should have been a quiet day in space weather. And yet the solar wind was running at approximately 549 kilometers per second. The KP index, the global measure of geomagnetic disturbance, had reached KP4, which is the lower boundary of active geomagnetic conditions. Electron flux at geosynchronous orbit was measured at 13,748 particle flux units, elevated enough to be logged and monitored by satellite operators. How do you get active geomagnetic conditions from a spotless sun? The answer is coronal holes. A coronal hole is a region of the sun's outer atmosphere, the corona, where the magnetic field opens outward into space rather than looping back on itself. Through these open field lines, solar wind escapes at elevated speed, carrying a stream of charged particles outward that, when Earth-directed, can interact with the planet's magnetosphere and produce geomagnetic activity even in the complete absence of solar flares or coronal mass ejections. Flare-driven space weather tends to be sudden and dramatic, a brief, intense burst followed by a coronal mass ejection that, if it hits Earth, can produce rapid storm onset and significant geomagnetic disturbance within hours to days. Coronal hole-driven space weather is different. It is slower, more sustained, and tends to recur on roughly the same 27-day rotation cycle as the Sun itself. If a coronal hole is facing Earth today, it will roughly face Earth again about 27 days from now, unless the hole has evolved or dissipated in the meantime. There is no confirmed mechanism linking coronal hole-driven solar wind streams to jet stream behavior or tropospheric weather patterns. That connection, when proposed, sits in the category of active research and contested claims. The honest position here is that over 3 consecutive days centered on February 25th, geomagnetic activity produced by an elevated solar wind stream from a coronal hole coincided with an exceptionally amplified atmospheric pattern, driving 616 simultaneous weather alerts. Is that causation? No evidence supports that conclusion. Is it coincidence? Almost certainly. Is it a question worth flagging? Given that this channel exists precisely to flag the questions, mainstream coverage doesn't always stop to ask, yes, it is. What we can say with confidence is that both the atmospheric pattern and the geomagnetic activity share a structural characteristic. They represent elevated, sustained energy input rather than a brief spike followed by return to baseline. The solar wind stream was not a one-hour event. It was a multi-day flow from a persistent coronal hole structure. And the atmospheric pattern was not a one-day event either. It began before the blizzard, persisted through the blizzard, reconstituted itself after the blizzard, and by February 25th was producing more simultaneous alerts than the blizzard peak itself had generated. Persistence in two separate systems operating at two separate scales. And 27 days from now, give or take the evolution of that coronal hole, the solar component of this picture may be worth looking at again. The Sun rotates approximately once every 27 days, as seen from Earth, technically a sidereal rotation period of about 25 days. But Earth is also moving in its orbit, so the apparent rotation from our perspective is closer to 27. Coronal holes rotate with the Sun. If a coronal hole is well positioned to direct its solar wind stream toward Earth today, the simple frequency calculation, 1 cycle per 27 days, suggests a potential recurrence window around late March. This is not a prediction. Coronal holes evolve. They can shrink, expand, or dissipate over a rotation period. Solar cycle 25, which we are in the declining phase of, is generally expected to see coronal holes becoming somewhat more prominent as activity from active regions diminishes, consistent with what we're observing with a spotless or near-spotless disk. Whether the specific hole responsible for the February 25th elevated solar wind will persist and maintain Earth-directed geometry through another rotation is genuinely unknown at this point, but it is a monitoring window worth noting, and it reinforces the broader theme here. These are not patterns that spike and vanish. They are patterns that persist, recur, and compound. The same persistence that makes a recurring coronal hole relevant is precisely what makes the atmospheric pattern we've been tracking so consequential. Which brings us to the question this entire story has been building toward. Is what we're seeing on February 25th, 2026, a natural fluctuation within normal atmospheric variance, or is it evidence of something shifting in how the atmosphere operates? That question deserves more than a dismissive answer in either direction. 616 simultaneous alerts, and the alert count went up after the storm that was supposedly driving it ended. Let's sit with that for a moment, because it's the detail that should be generating the most serious discussion in atmospheric science right now. And it's the detail that tends to get lost when media coverage tracks individual extremes rather than the system producing them. A compound extreme event is defined, broadly, as the coincidence or rapid succession of multiple extreme weather or climate events that produce impacts more severe than any of the individual events in isolation. The concept has gained significant traction in research over the last decade, precisely because infrastructure, emergency management, and adaptation planning tend to be designed for single hazard scenarios. A power grid designed to handle a major ice storm can be overwhelmed if that ice storm arrives on top of a wind event that has already strained the system. A flood control system designed for a major atmospheric river can fail if the watershed is already saturated from a preceding precipitation event. Emergency resources deployed for a blizzard response cannot simultaneously manage wildfire evacuations, marine search and rescue operations, and flood emergency coordination. The 616 alerts on February 25th were not 616 versions of the same problem. They were distributed across hurricane-force marine wind, coastal flood, river flood, blizzard and winter storm, high wind, red flag fire, and extreme heat categories. That multi-category distribution means that the National Emergency Response Architecture was being asked to address genuinely different kinds of emergencies simultaneously in different regions with different resource requirements. There is no pooling of fire suppression aircraft to help with flood rescue. There is no redirecting of Marine Coast Guard assets to assist with mountain avalanche rescue. Now, a legitimate caveat is necessary here. The National Weather Service has expanded and refined its alert categories significantly over the decades. Some portion of any increase in alert counts over time reflects improvements in detection, modelling, and the institutionalization of new warning types rather than purely a change in atmospheric conditions. Alert inflation is real, and anyone who ignores it is not being straight with you. We should be honest about it. But the multi-category spread of February 25th alerts is harder to dismiss as a product of category inflation. The events themselves, the 83-mile-per-hour gusts at Dakota Hill, the Eel River flood stage breach, the hurricane-force marine warnings in Alaska, the Northern California atmospheric river, the near-record heat in Southern California, are real, measurable, instrument-verified phenomena, and their simultaneity, tied to a single pressure gradient superstructure, is what makes February 25th a legitimate case study for compound extreme research. What the research asks and has not yet definitively answered is whether events like February 25th are increasing in frequency, in intensity, or in geographic scope. This is made more complex by the fact that what matters may not be the average condition, the mean, but the variance. A world in which the average February temperature is 1 degree warmer may be less consequential for infrastructure than a world in which the amplitude of temperature swings from week to week has increased, even if the mean hasn't shifted dramatically. Sharper contrasts, not just warmer averages, may be the more consequential signal to watch. Since the blizzard days ago, this pattern hasn't relaxed. It has restructured. It has maintained its amplitude, rotated its hazard zones, and produced more total alerts at the post-blizzard stage than it did at the blizzard peak. That is persistence. And persistence, in the context of compound extremes, is what converts individual events into sustained infrastructure stress. The jet stream is the governor of all of this, and whether the jet stream is changing or whether we are simply experiencing the natural range of its variability is one of the most contested and consequential debates in atmospheric science right now. The jet stream is a narrow band of fast-moving air in the upper troposphere, driven by the temperature contrast between the tropical and polar regions of the planet. It flows generally from west to east at altitudes between 25,000 and 45,000 feet, and it is the organizing structure that determines where storm tracks develop, where cold air masses push south, where warm air is advected north, and how long any given weather pattern persists before being swept downstream by the flow. Under normal conditions, the jet stream maintains a roughly zonal flow, moving primarily east-west with modest northward and southward undulations. Rossby waves are always present in the jet, but their amplitude and phase speed determine how extreme and how persistent any given weather pattern becomes. Large amplitude waves develop deep ridges and troughs. Slow-moving waves allow those ridges and troughs to sit over the same regions for extended periods. Persistent ridges and troughs mean persistent weather. Prolonged drought under a persistent ridge, extended cold snaps under a persistent trough, repeated flooding from systems that keep arriving in the same corridor. The scientific debate about the jet stream centers on a hypothesis that has gained significant attention over the last 15 years, associated with researchers including Jennifer Francis and Stephen Vavris, among others. The core argument is this. As the Arctic warms faster than the rest of the planet, a phenomenon called Arctic amplification, which is observationally well documented, the temperature gradient between the tropics and the Arctic weakens. Because jet stream speed is tied to that gradient through thermal wind balance, a weakened gradient produces a slower, more meandering jet. A slower, more meandering jet develops larger amplitude Rossby waves. Larger amplitude waves move more slowly, persist longer, and produce more intense impacts beneath them. This hypothesis, if correct, would provide a mechanistic link between long-term global temperature change and the kind of amplified, persistent, multi-hazard atmospheric pattern we observed on February 25, 2026. It would suggest that events like this, not just warming, not just individual extremes, but the simultaneous stacking of contradictory extremes driven by high amplitude, slow-moving wave patterns, might become more common as background conditions continue to evolve. But the hypothesis is contested, and that contestation is legitimate. Some research groups argue that the observational evidence for jet stream winding is inconsistent across datasets and time periods. Others argue that natural variability, particularly the phasing of El Niño Southern Oscillation and the Pacific Decadal Oscillation, which are known to influence ridge and trough position over North America, can produce patterns indistinguishable from what the Arctic amplification hypothesis would predict, without requiring any change in the climate background state. A deep La Niña, or a positive Pacific Decadal oscillation phase, can anchor a persistent ridge over the western United States and a persistent trough over the eastern United States for weeks at a time, producing exactly the kind of split we've been describing. What makes the scientific debate genuinely difficult is the signal-to-noise problem. The climate system is noisy, natural variability is large. Detecting a trend in wave amplitude or jet stream speed that is statistically distinguishable from natural fluctuations requires either very long data records or very clear signals, and the literature currently has significant disagreement about whether the signal of Arctic amplification on the jet stream is yet detectable above the noise. What is not in dispute is that the pattern we observed on February 25th did not resolve after the blizzard. It persisted. It evolved. It restructured its hazard distribution without losing its fundamental amplitude. The ridge stayed where it was. The trough stayed where it was. The gradient between them, which is the engine of everything we've described, remained steep enough to keep 616 simultaneous alert products active and rising. Whether that persistence is a signature of something new in the climate system or a particularly intense manifestation of natural variability, that question does not have a settled answer. But it is the question that February 25th, 2026 is forcing the scientific community to take seriously. Here is a distinction that rarely makes it into weather coverage, but may be the most important concept for understanding what a pattern like February 25th actually tells us about where the climate system is headed. When we talk about climate change in popular coverage, we tend to talk about the mean, the average. Average temperatures are rising, average sea levels are rising, average precipitation patterns are shifting. These mean shifts are real, documented, and consequential. But there is a second statistical dimension that may matter more for infrastructure, for emergency management, and for the day-to-day experience of living in the atmosphere: variance. A variance shift means that the distribution of outcomes is spreading out, that the extremes at both ends are becoming more extreme, even if the average doesn't change dramatically. In a world with increased atmospheric variance, you don't just get warmer averages. You get larger swings, you get deeper cold outbreaks alongside more intense heat waves, you get heavier precipitation events alongside more prolonged droughts. You get larger temperature contrasts across shorter distances. In other words, you get amplified ridge-trough configurations producing 100-degree continental temperature spreads and 616 simultaneous alerts. The climate system is non-linear. Small changes in background conditions can produce disproportionately large changes in the frequency and intensity of tail events. This is not the same as saying the atmosphere is becoming apocalyptic. It is saying that if the variance of the system is increasing, if the oscillations around the mean are getting larger in amplitude, then the infrastructure designed to handle the historical range of atmospheric variability may be systematically undersized for the new range. February 25th, 2026. Maybe, in the long view, a data point in a trend toward higher variance, or it may be an outlier event in a system that has not fundamentally changed. Both possibilities are consistent with the current state of the science. What is not ambiguous is that the 616 alert pattern did not look like normal background noise. It looked like signal. Whether that signal is telling us something durable about the atmosphere's future behavior is the question that the data from days like this will eventually help answer. The pattern is ongoing, which brings us back to the beginning: 616 alerts, active, simultaneous, and rising after the blizzard that was supposed to be the story ended. Let's come back to that number one more time, because it is not just a quantity. It is a description of a system state, an accounting of how many places across the United States were simultaneously in conditions dangerous enough to require formal public warning on February 25th, 2026. Hurricane-force winds over the Gulf of Alaska, with seas approaching 20 feet. Near-record heat pushing 90 degrees across Southern California in the last week of February. Rivers running toward flood stage across Northern California, fed by a moisture plume so anomalous that the National Weather Service felt compelled to flag it in the language of statistical extremes. 83-mile-per-hour gusts, active fire danger, and 20 inches of snow within 100 miles of each other in Colorado. A cold dome sitting over the northeast, still generating snow from clippers and lake effect systems. A lingering ghost of the blizzard that was supposed to have moved on. And in space, a coronal hole streaming solar wind past Earth at 549 kilometers per second, nudging the geomagnetic environment toward elevated activity under a sun that looked, by every standard measure, like it was doing almost nothing. Every item on that list, every single alert, every single regional extreme was connected to one amplified pressure gradient superstructure. One ridge, one trough. One steep thermal contrast stretching from the Arctic air mass over the central and eastern continent to the warm, moist air mass over the western interior. The mechanism is not mysterious. Rossby waves, thermal wind balance, pressure gradient force. These are not fringe ideas. They are the foundational physics of atmospheric dynamics, the same equations that weather services around the world use every day to generate forecasts. What is not routine is the magnitude. What is not routine is the persistence. The pattern didn't end when the blizzard ended. It didn't resolve when the snow stopped falling on the East Coast. It reconfigured. It redistributed its energy. It changed which face it was showing, from blizzard to a simultaneous multi-hazard pattern that drove the alert count higher, not lower, in the days that followed. That evolution is the detail that should make anyone paying attention uncomfortable with easy answers. Looking ahead from February 25th, Day 6 and Day 7 forecast models were showing a split in ensemble agreement about the next winter storm developing over the western United States, which means forecasters were working with high uncertainty about where the next significant event would arrive and how intense it would be. Southern California's near-record heat anomaly needed verification. The forecasts were remarkable enough that operational meteorologists were watching closely to see whether the models were capturing something real or running warm. The overall alert count, would it normalize? Would it continue rising? The behavior of that number in the days following February 25th was a direct read on whether the pattern was maintaining its amplitude or finally beginning to relax. And the coronal hole, 27 days out from a well-positioned coronal hole stream, late March would present another potential monitoring window for elevated solar wind and geomagnetic activity. None of those open questions come with clean answers on February 25th. That is not a failure of meteorological science. That is what a genuinely complex, genuinely amplified, genuinely unresolved atmospheric pattern looks like in real time. Here is what we know. The mechanism is understood. The physics is not in dispute. The Rossby wave produced the gradient produced the winds, the fire conditions, the orographic snow, the atmospheric river, the compressional warming, the subsidence heat, and the marine cyclone. One structure. 616 simultaneous expressions of it. What we don't know is whether patterns like this are becoming more common, more intense, more persistent, or whether February 25th, 2026 will look, in retrospect, like a bad day in a variable system rather than a harbinger of a system whose rules are quietly changing. The data will accumulate, the models will be evaluated, the research will continue. But here is what keeps atmospheric scientists up at night. Not the storms themselves, not the alerts themselves, but the possibility that the atmosphere is not just varying around a fixed center anymore. That the center might be drifting, that the oscillations might be getting larger, that the events we call extremes might be rehearsing at increasing frequency for a range that used to be reserved for once-in-a-generation outliers. 616 alerts. The mechanism is known. The magnitude is uncertain. The pattern is ongoing. And somewhere in that gap between what we can explain and what we cannot yet predict is the most important question the atmosphere has ever asked us. We just haven't figured out the answer yet.